let's look at this. Here's one of the equations of motion. You might recognize it. Anybody recognize that? Do you know what the symbol stands for? S stands for, distance or displacement. Don't let Ed do all the work here. S, displacement. Distance is the scalar version. Displacement is a vector version. What's the difference between the two? Somebody apart from Ed, because I know Ed knows. No, displacement is the vector. Distance is the scalar. What's the difference between scalar and vector quantities? Correct. So if I measure the displacement, I must also give a direction. So 3 meters at an angle of 30 degrees would be the displacement. 3 meters is the distance. So they're often interchanged, but really there is a difference between the two. So we might measure that in meters, something like that. What does the U represent? Ed? The initial velocity. A is the, no, it's a clue in the letter, acceleration. And finally T, time, right. How many variables in that function? No, 4. S, U, A and T. So every time a letter appears in a function or a formula, that's a variable. That's something that can change. Remember what S, U, A and T are. They represent numbers, so each of those could be a number and that number could change. 4 variables in this function. I'm interested in how displacement changes with time. So I want to plot this on an autograph. What is the independent variable going to be? Time, okay? So that's going to go on the x-axis. I'm interested in how the displacement changes with time, so what's going to go on the y-axis? The displacement. So therefore, U and A must be, right, okay. So let's plot this on autograph. So what am I actually going to plot on autograph? Here's the original formula. What am I going to plot on autograph? That's supposed to be a plus, yeah. Right. So that's exactly what I'm going to plot on autograph, because T is my independent variable, X and S is my dependent variable. If I plot it, what might I expect it to look like? Yeah, because of the x squared term, it's going to be a quadratic, so I'm expecting a curve. Yep. Close this. Open a new page. And I'm going to type in y equals ux plus a half So let's put 0.5 in for the half. A x squared. Hit OK. And we get our curve. Okay. I'm only interested in the curve beyond the x-axis, on the positive side of the x-axis. I'm not interested in negative times. So often that's the case when I'm looking at a function in an engineering situation. I'm only interested in this quadrant. Not always, but often. Okay. I can't see an awful lot at the moment, so let's zoom in on the zoom out rather on the y-axis so that it can stretch itself across this x-axis a bit more, and we can see a bit more. So that's what's happening. So what we have here, remember what we're plotting. We're plotting x, which is time, against displacement. What autograph has done, though, is it's assigned values to u and a, because remember, u and a are constant. So if we look back at this, u and a are constant. So we need to find out what they are, actually, before we can put that into autograph. Yeah. So autograph, though, gets round that by just, by default, assigning these constants, u and a, as 1. So although we've got the shape of the curve, we haven't really got the right curve because we've not got the values for u and a. It's going to look like this, but it won't give these numbers. Sorry? Yeah. It's the right curve, yeah, but what it's done is it's assigned u to be 1 and a to be 1. And that this particular software does, yeah, it automatically gives it a 1. It doesn't say to you, you need to put in u and a, it just gives it the value 1. Different software might do different things. So what we've got to do now for this particular problem is to find out what u and a are. And that's where the simultaneous equations come in. So let's go back to this for a minute and think about what we're going to do next. So although we've got the shape of the curve, we need u and a values for u and a, really. To be able to use it. So we do an experiment. This function could be describing something it's describing something accelerating, and we're looking for the displacement. So some moving object. I mean, I'm automatically thinking of a vehicle moving along, but it could easily become some sliding component going up and down the machine with a constant acceleration and starting with an initial velocity. The initial velocity might be 0, but it might not. Okay? So what we need is some values. So we do an experiment. We set the thing moving, and we have a stopwatch, and we've marked out some displacements, some distances. So we start the thing going, and we notice that, and these are just some figures I worked out. So after a particular time, 13.68 seconds, so it's been measured pretty precisely, we find the displacement equals 918.344. So it's been measured to the nearest millimetre, so this is a pretty, accurate experiment. How far it's gone, yeah. So we set the thing going, we notice after that time it's gone that distance. That's two unknowns, S and T. So to get the values for these, we need another equation. Two unknowns, two equations, simultaneous equations. So we also note that after 68.4 seconds, the displacement, so it's moved further, and it's now gone to a displacement of 22950, 0.39 millimeters. So now we can form two simultaneous equations and plot them to solve. What will those simultaneous equations look like? We've got the original formula, here it is, to remind you. So what am I going to do with those values? Put them in, yeah. So S, for the first situation, S equals 918.344 and T equals 13.68. That would be equation 1. And for equation 2, S equals that and T equals 68.4. So write down your equations 1 and 2. And you might get something like that for equations 1 and 2. I've put the U after the 13.68 here because algebraically we tend to put the number first and then the letter. So that's the only reason I've done that. It's the same thing. We can simplify this a bit by working out what a half of 13.68 squared is and what a half of 68.4 squared is. So let's do that. So work out what we can, simplify it. Autograph doesn't like you to put in complicated things like that, so work out what you can, and that's the answer. So now we've got two simultaneous equations. What are we going to do with them? We've got to try and solve them to find U and A. So what do? Put it into autograph. Yeah, it's one of those cases we're not going to try and solve these algebraically. We're going to bang them into autograph because we've got it available to us. But we can't type that into autograph because you need only recognise as X and Y. Yeah, so that's your point, Sam. It's entirely up to you because it doesn't matter which one you call X and Y in this environment. We're just after two unknown values. So let's say assign U to be Y and A to be X. So I would actually put into autograph equation 3 with Y and X instead of U and A and equation 4. Okay? Okay. So we type them in. There they are. Initially you can't see it, and you found it by looking. You zoom out basically until you see something, and there the line starts to appear. Now I want to focus in on one particular part, so I can use this box to focus in on this particular bit where they cross here. If the lines start to go very close to each other, which they are in its vertical sense, that means to me that everything is happening over a very small period on the x-axis. So if I want to spread that out, I need to zoom in on the x-axis. So if I want to separate out these lines, I zoom in on the x-axis and then the lines move apart a bit. And then you can get a clearer indication of where they meet. So again, I could use the zoom box to go in and zoom in on these values. And you can see that what we're saying about one of the disadvantages here is you don't get exact answers. So you can come up with an answer. So if I say, right, I want an answer to about 2 or 3 significant figures, I'd have to keep zooming in until I've got 2 or 3 significant figures in my answer. So if you could do that, please. One word of warning on this, every now and then it crashes the program. So once you've got something half decent like this, I'd recommend you save it. Yeah. I recommend you save it, and then if it crashes, you can at least find it, okay? It just stops working sometimes, so be careful of that.